This is Lesson 7 in Unit 6. Today's lesson is all about inverse relations and inverse functions. You might recall that inverse operations undo each other. And when we have a relation that has an ordered pair, AB, then the ordered pair BA is in the inverse. Now, the inverse could be a function, or it could be just simply a relation. An example of an inverse function, let's say we had the function f of x is x plus 3. The inverse function, f inverse of x, is going to be x minus 3. And you can explore those properties later at the end of the lesson. If you have function f and f inverse, and they are inverse functions of each other, then the composition of f inverse f of x and f of f inverse of x, if both of these compositions give you the identity function y equals x, then f and f inverse are inverse functions of each other. Another way we can say the same thing, for example, if I let f of x, if I let y be my f of x, and I let g of x represent the inverse function, f inverse of x, then the composition, we could say, without this complicated notation here, we could say that the f of g of x is equal to the g of f of x if they both equal x. This is my identity. So if we do the f of g of x and we get an x, and we compose the g of f of x and we get an x, then we know that f and g are inverse functions of each other. Here we're going to look at inverse relations. We have these ordered pairs, -2, -2, -1, 1, 0, 2, 1, 1, and 2, -2. You can see that that's points from a parabola. Now, if we take that inverse relation and take this y column and it becomes our x column in the inverse relation, then our x column becomes the y column in our inverse relation. We want to go graph those. We'll switch colors to red, and we can graph -2, -2, so it passes through this same point. +1, -1, 2, 0, 1, 1, and -2, +2. So this is an inverse relationship. And in this particular exploration, we're asked, is S a function? So if you think about the vertical line test here on the blue graph, and you pass that vertical line across the blue graph, that relation S of x, yes, that is definitely a function. So we can say S of x is a function. It passes the vertical line test. But when we look at the inverse relation and think about passing that vertical line across the red function for every point except at the vertex, we're hitting one point here, but everywhere else on our red graph, we're hitting more than 1 point. So the inverse is only a relation. S of x is a function. It passes the vertical line test. But the inverse relation is only a relation since it fails the vertical line test. Okay, so S of x is a function, but the inverse is simply a relation. It's not a function. In example 2, we want to find an equation for the inverse. And by that, we mean we want to switch, since the ordered pairs x, y are in a function, then the ordered pair yx is in the inverse. In other words, we are switching the x and the y. That's our first step, to switch the x and the y. Switch x and y. And from there, you would want to solve for y and isolate the y variable. So when we solve for y, subtract 3 from both sides, divide both sides by 2, and we've solved for y. Now, this y here is different from our original y up here. So it's customary when you have an inverse function and you know it's a function, you want to change the y to the proper notation and use f inverse of x for the new y. And in this case, we started out with a line. That line is a function, and our new function, f inverse, is also a function. It's just another line, a half times the quantity x minus 3. This is an inverse function. In example B, we've got something different. So we're still switching the x and the y, but this is like our exploration. We've got a parabola, and the parabola is a function to start off with, but when we get to the inverse, it's going to be just a relation, and we won't be able to use inverse notation like over here in example A. So let's solve. We switch the x and the y. Now we're going to solve for y. And here's where we're going to fail, because we want to take the square root of the y squared. That'll give us the y. But anytime you introduce the square root function, you have to consider you have both positive and negative square roots. So our y equals positive and negative square root of x. If you wanted to be able to use inverse notation, then the inverse notation for the inverse function would only be the top part of the square root, not the bottom part of the square root. That way we're keeping the second part, the negative square root, that would not be part of the inverse function, only the top part. This is a relation only when we leave our answer like this. It's not an inverse function. This is the inverse function up here, and it's going to have some domain restrictions. We'll see that in our next example. So you can see we're going to graph 2a and its inverse in example 3 right here. So graphing 2x plus 3, the y-intercept's at 0, 3, and the slope is 2. So this is our function, y equals 2x plus 3. But our inverse function has an x-intercept at 3, and the slope is 1/2. So we can rise 1 and run 2 in both directions. And this is our inverse function here. This is f inverse, and this is f of x. Now, do you see how the y equals x when we do compositions? This is the line, y equals x. It goes through the diagonal. That's our identity. That's how you can tell these are inverses of each other. The point 3, 0 is on the red graph. The point 0, 3 is on our blue graph. In example B, we have x squared plus 1. So we've got a parabola that's shifted 1 unit up. This is our parabola. That's our f of x. But if we graph the positive square root of x plus 1, that's this one, the top portion. This portion is the inverse. But the bottom portion is what breaks our problem into only being a relation. This piece down here, the sideways parabola, is not a function. It's only a relation. So in example 4, moving on to that, how do you find the inverse? What are the domain and range of f of x? Well, f of x is the square root of x plus 2. So you might know that this is a parabola, a half of a parabola, or the square root function, shifted 2 units to the left, and it looks something like that. So our domain, we know that the domain is going to begin at -2. It includes -2 and goes to the right forever, so 2 to infinity, including -2. And the range, since -2, 0 is our beginning point, the range is going to begin at 0, including 0, and goes up. We want to find f inverse. So to find f inverse, we're going to take the y equals radical x plus 2, and where there's a y, we'll call that x. Where there's an x, we'll call that y. Then we're going to solve for y. So we want to square both sides, and when you square a square root, they undo each other, and y plus 2 has escaped. Now, we've got the inverse, f inverse, is x squared minus 2. And the reason that we have a parabola here, you can see from part A, the domain of this function started at -2, and the range went from 0 up. So our reflection is going to have to be only the part that's positive or includes 0. We've got a restriction on that function. So you could say that this is the inverse for x greater than or equal to 0. Then on part C, the domain and range of the inverse, we're going to see that the domain of the function is the range of the inverse, and vice versa. The domain is going to go from 0 to infinity on the inverse function, and the range will be from -2 to infinity on the inverse function. And we should probably put a note in our lesson here to indicate that the domain of the function, the domain of the inverse, is the range of the original function. They flip-flop. If we interchanged x and y, then we need to interchange the domain and the range. And f inverse will be a function. This is our explanation. If the domain for the inverse is restricted to all the values of x being 0 or greater. Now, we can say a function is 1-to-1 if all the elements of a and b in the domain of the function are not the same. A isn't b implies that the y values aren't the same. In other words, that is that different values of the domain have different values of the range. If the graph of a function is known, we can use the horizontal line test to determine whether a function is 1-to-1. So it's the horizontal line test That tells me if I have an inverse function. If every horizontal line intersects the graph of the function in only one point, then f is going to be 1 to 1. Okay, let's take a look at the properties of inverse functions. So here's what we've seen. Graphs of inverse functions are reflections in the identity function, which is y equals x, the line y equals x. When you're given a function, f of x, the notation for the inverse function is f inverse of x. That's our new y. The domain of a function is equal to the range of the inverse, and the range of a function is equal to the domain of the inverse. And here we can see those properties again. This is our line y equals x. It's the diagonal or identity function. Here you can see the ordered pair 3, 1 is on the inverse, and that's true because the ordered pair 1, 3 is on the function. And if you consider the black line, think about passing a horizontal line across here. The black function is 1 to 1, which means the inverse function is going to be a function that passes the vertical line test. The blue graph passes the vertical line test because the black function passed the horizontal line test. Let's take a look algebraically and determine whether the pair of functions are inverses of each other. And remember, this was when we're going to do compositions. So we want to see what happens. Does f of g of x give us x? That's our problem. So f is 1/2 x plus 5. And where this x is, this is my space here, I need to go put the g function in that place, 2x minus 10. So my question is, when we simplify that down, does it give us just x? So distributing, half of 2x is x, half of 10 is 5, and then add 5, we do get x. So the f of g of x gives me x. But we can't just simply stop there. We have to do the composition the other way to verify. So the other way would be to use the g of f of x, and the g of x is 2x minus 10. So here in this place, we're going to go get the f of x and put that in its place, which is 1/2 x plus 5. So distributing the 2 to the half x gives us 1x, and distributing 2 times 5 is 10. X plus 10 minus 10 gives me x, so the g of f of x is also x. If one composition gives you x and the other composition gives you x, then we can definitely say yes, f and g are inverses of each other. Example 6 is a little tricky since we're going to need to complete the square. We have y equals x squared minus 4x minus 1. Now that's not a perfect square. And we're going to interchange the x and the y, and that'll help you see the need for why we need to complete the square. So I'm going to set it up and move the minus 1 out here. So here's our problem. I need to be able to get the y's together, and there's no way to combine those terms. So whatever we do, we need to make it a simpler problem. Completing the square, if we take half of 4, that's 2, and 2 squared is 4. So if I add 4 here, I want to subtract 4 here. That way we have a perfect square trinomial which factors as y minus 2 quantity squared. And then -1 minus 4 makes -5. So this way we can very easily get our terms together and isolate the y. Add 5 to the left and 5 to the right, and then we have all the y terms on the right, but we've got to take the positive and the negative square root of x plus 5 when we take the square root of the binomial squared. So we have y minus 2 is equal to the plus or minus square root of x plus 5. So y is equal to 2 plus the square root of x plus 5. This one is our inverse. And y is equal to 2 minus the square root of x plus 5. So this one is our f inverse. And we're going to graph the x squared minus 4x minus 1. And if you know the properties of parabolas, you know you can find the vertex as half of the b value divided by 2, opposite b over 2a, which is 2, and then substitute that back in. We would have 2 negative 5 for the vertex on the function f of x. And because the a value is 1, it's going to follow the 1, 3, 5, 7 pattern for 1, 2, 3, 4, 5 for movement up and right and left. Okay, so there's our f of x. But we only want to graph f inverse of x, because it said graph the function and the inverse. And the inverse has to be a function. That's the positive square root of x plus 5. So we've got a square root function that shifted 5 units left and 2 units up, and it follows the 1 up, 1 right, 1 up, 3 right, 1 up, 5 right. So this is the inverse function. This is f inverse. Okay? So if you wanted to, you could restrict the domain on the parabola and only graph the portion that's a mirror image of the inverse, and you would have a picture like that. If I leave it, you can see that the f of x is a function. It passes the vertical line test, but f of x is not 1-to-1. It fails the horizontal line test. Only by restricting the blue graph will f inverse pass the vertical line test to be a function. Our last two examples are application problems. If we want to convert degrees Celsius to Fahrenheit, we can use this formula. So to find the inverse function, f inverse, we could say that x is 9/5 y plus 32, and we're going to subtract 32 from both sides and then multiply through by 5/9. So our inverse function is going to get y alone. We would have 5/9 times the quantity x minus 32. If our function f of x converts Celsius to Fahrenheit, what does the inverse function do? Well, we can say that the inverse function will convert Fahrenheit degrees to Celsius degrees. Okay? Because they undo each other. One formula gives you Celsius when you have Fahrenheit. that's our inverse. The other formula gives you Fahrenheit when you have Celsius. And then our last example, the function d equals 4.9 t squared represents the distance in meters that an object falls in t seconds due to Earth's gravity. And we want to find the inverse of the function to be able to use it. Now, in this case, I'm not switching the d and the t. I'm simply going to solve for the t squared using inverse operations. That way I can use the t formula in order to find something based on some given information. And here's what we know. We want to figure out how long it takes in seconds. So we've got the t isolated here in our formula on this line. We want to know how long it takes for a cliff diver to hit the water if he falls 30 meters. So the time it takes to go 30 divided by 4.9 under the radical. If your calculator is handy, you can do that calculation and find the time is about 2.5 seconds to fall 30 meters, which is roughly 90 feet. That makes me think about the men in Mexico, in Acapulco, that dive off of the side of the mountain. It's a pretty interesting sight. Okay, that's the end of Lesson 7. I'll see you next time.